Hey, does any of you have an iPad dongle that I can use to connect to the projector? Sort of an iPad adapter. I can't seem to find mine. It's oh yeah, I think this does.
USB on one end, and the other end is.
Yeah, I think this is different. Yeah.
Oh, different.
It's yeah. Thanks.
It doesn't work right. Okay.
Thanks.
So you may ask.
Alternately, if any of you have a writable tablet that I can borrow with a USB-C, I think there's USB-C over here.
Do you have a laptop by any chance? You too? No? Okay, that's fine. Okay, this is sorry. Yes. Okay, so yeah, I have Notability. I don't know what kind of... Like, this is probably fine, right? Okay. Notability, yeah. Okay. I guess, best place, you could just leave it, you know, the fourth floor alcove soda? Just after lecture, just put it, because my office hour is like at 6, so... Okay. I'll be at soda at like 6, so...
You can be at soda at 6.
Okay, alright, cool. So, it's on the other side. you know how to get colors if you need colors? It's just here. Just do like here. And it's different colors. Oh. So you can do straight lines if you like holes. That's kind of slow. Do you want a piece of paper? Is this better?
Just do this.
Okay. Okay. Foxy. Man, I forgot how to do Foxy.
And then the next page is just keeps going
It
down.
just keeps going down. You just keep writing. Okay, we're good.
Okay. All right. So Max saves the day again. Let's thank Max for the. All right. Let's begin. Oh. I hope. This is the VGA. What happened here? Right, this says it's
It does say it's connected, right?
yeah. This is not.
I mean, this is a VGA. You have it to VGA?
Yeah, I do.
Oh, yeah.
Maybe just take it out and put it in.
It says it has it again.
Um, okay, let's start. Yeah, my apologies for the mix-up. I don't know where I dropped my iPad dongle, and it's. Okay, so let's. Okay, it's been a while since I lectured. We've been talking about more and more powerful algorithms in the class. We talked about dynamic programming, linear programming, and it's always been a success story that we can solve this problem efficiently, and so on. What we'll start doing now is looking at problems that are really much harder. in that we probably cannot solve those problems efficiently. And we'll try to say what we can about them. So this is going to be a couple of weeks when we talk about these issues of interactability. But so today we'll start talking about it with the in the context of the NP versus P problem. Okay, so I need to define what NP and P are. Well, basically, NP and P are, you could say these are classes of computational problems. Okay, and in particular, P is our notion of what's efficiently solvable. So what is P? P is the class of problems for which one can find the solution in polynomial time. Okay, so I know I'm being a little vague here in that I'm not formally defining P here, but there is a formal definition of P. We just will not do the formalism in this class, but we will do we will do enough to, or we'll see enough examples to understand what the formalism is trying to do. So, in particular, for now, let's just say P is the class of problems for which you can find the solution in polynomial time, like minimum spanning tree is a problem which you can solve in linear time or close to linear time, and that's a problem here. Okay, shortest paths, and all of the problems that we studied in this class so far are problems that you can solve in polynomial time. And why do we care about polynomial time? Well, polynomial time will be our notion of efficiency. So when we say an efficient algorithm, we'll mean polynomial time. Okay, polynomial as in some n to the c for some fixed c, so n squared time, n cubed time, or n to the 100 time. Of course, is n to the 100 time really efficient? No, right? On an n to the 100 time algorithm, you can't even run it on an input of size 4, right? But we'll still call every polynomial time algorithm efficient. So first, a little bit of justification why we do this. Well, empirically, it's been the case that usually when a problem is solved in polynomial time, the algorithm initially probably takes n to the 20 time, but over time, the algorithm gets improved into something linear or quadratic or something very reasonable. And this is just an empirical fact. It's not a formal fact, but just it's an empirical fact that most interesting problems, once they have a polynomial time algorithm, they have a very good efficient algorithm. So in that sense, polynomial time is a good proxy to say when is something efficient or inefficient. But there's another reason why we would say polynomial time is efficient. It's just that we want to study, let's say, the landscape of how hard different problems are, the landscape of computational complexity. So, it's a very complicated landscape, and it's really, really difficult to formally prove lower bounds here. So, for instance, fast Fourier transform takes n log n time, and after 50 years, we still can't prove that you can't do any better, right? So it's really hard to prove lower bounds. So let's be less ambitious and try to understand this landscape at a very coarse level first before we go into the fine details of whether it's n squared or n cubed. Let's just try to understand it at a coarse level. Okay, is this problem solvable in polynomial time or not? Is it polynomial or exponential? Even at this very coarse level, you'll see lots of interesting structure come up and lots of interesting open questions. So that's the reason. In some sense, we talk about polynomial time. One, it's a good proxy, but the other is just that let's start doing something that is simple first, and before we ask very precise questions of the runtime of different problems. Okay, so I don't need to say more about P. Let's talk about NP. So NP is not polynomial time. Then it would be a super easy question. P is not equal to NP. But NP is really the problems for which you can verify the solution efficiently. This is a class of problems for which verifying the solution is easy. Easy as in solvable in polynomial time. You can verify in polynomial time. Okay? So let me give you an example. So the first example I'll describe is the 3 coloring problem. So what is this problem? Well, the input is a graph. Okay? And the solution, I'll use the word solution instead of goal. What's a solution here? A solution is a coloring of the vertices of the graph with 3 colors. So I've given you a graph, and what you want is to assign a coloring. What's a coloring? It's just going to be a map, C, from the set of vertices to 3 colors, let's say red, blue, and green. So you want to assign 3 colors to, one of 3 colors to every vertex, such that each edge gets 2 different colors. Okay. For each edge, the endpoints get different colors. So I guess the classic problem is if you have a map and you want to color the countries in the map, you don't want neighboring countries to get the same color, right? And a very classic theorem is that every map on the plane can be colored with just 4 colors. So here we're given a graph and we want to do the same thing. Every node we want to assign one of 3 colors, and we want neighboring nodes to get different colors. Okay? So this is a problem, and we know what the input is, what the solution is. So I claim that 3 coloring is in NP. 3 coloring is an NP problem. So why is that? Well, basically because 3 coloring, it's easy to verify a solution to 3 coloring. Okay, what I mean is, right, look at the following verification task. So you want to verify what? Well, you get the input. The verification algorithm gets the input, which is the graph G equal to VE. Okay? And it also gets the solution. Right? It gets the input and the solution, which is the coloring. Okay? And it just needs to check if it's a solution to this instance. It's a very easy thing. So what does it have to do? In this case, for 3 coloring, it just needs to do the following, right? It needs to go over every edge. For each edge, E equal to UV. It just needs to check if C of U is not equal to C of V. So you can do it in linear time. So it's really easy to check whether a coloring is 3 coloring. Okay? So, and that's why the problem is in NP. Okay, once you have an algorithm that can check the solution, the problem is an NP problem. Okay? Okay. So let's, I'll show you a few more examples of problems in NP if there are no questions at this point. Yes?
So are P and NP disjoint?
Yeah, that's the question. Right, so the question is, great question. So the question was, are P and NP disjoint? Okay, so disjoint. Okay, let's tackle that first. Okay, the question is whether P and NP disjoint. Any answers for that? Yeah.
For the minimum spanning tree, I think you say it can be like solved in linear time, but it's also really easy to verify.
Yes.
Just make sure
Every word. Yeah. Exactly. So the question was, are P and NP disjoint? So let's just, the answer is also worth just going over. So if you take something like the minimum spanning tree, okay, of course this is in P because we saw that in the class, but it's also in NP. Why? Because how do I verify that given an input, which is a graph, and a tree, which is a T, you want to verify that T is a minimum spanning tree of the graph G. Okay? I guess there are many. You could actually go into the structural characterization of how a minimum spanning tree looks like. Maybe you look at every cut, or you can do something like that. But an easy solution would be the following. Well, if a problem is easy and you want to check the solution, you can just solve the problem yourself and see if you get the same answer. Right? So in this case, what you could do is you could run the minimum spanning tree algorithm on the graph G. Right? Run MST on G, MST algorithm on G to get a tree T star. You might not get back the same tree, get a different tree. But then what do you need to check? Just that the cost of T star is the same as cost of T. Right? If you check that cost of T star is the same as cost of T, that shows that the tree T is also a minimum spanning tree. Okay? Question?
For problems that, like MST, that don't have a unique solution, but where it's harder to check if two solutions are equivalent, is there a nice proof that they are both in P and NP?
Okay, so it's a good question. Okay, Let me say what I'm going to say now, and then I'll come back to that question. Okay, so here's the rough thing I was about to say. I was about to say the following: that basically, by the following heuristic argument, if you can, oops, what was that? Sorry. Okay. Look at the following heuristic argument. If you can. Okay, yeah. Whoa. That's. Okay. Okay, this is. Okay, I'll just pick this. Okay, good. So if you can compute the solution efficiently, right, then you can just compute the solution and check that if you get the same answer. And so that way you can also verify the solution efficiently. So in a sense, P, the class P, is a subset of the class NP. Okay? So this is true. This class P is a subset of the class NP. And there was a great question, well, what if this heuristic argument is somewhat iffy because when you compute the solution efficiently, you might get something else, and how do you know that the other one is also a solution? I'm sure there are cases where that can happen and you can't really check, but some of these issues are just because of the way we are defining P and NP in this class. But in the sense that we are not defining them in terms of decision problems, we're defining in terms of search problems. But bear with me that once you define it as a decision problem, you will have P's in NP. But at a high level, this is basically the fact. The fact is if you can compute the solution efficiently, Well, you can check that you got the same solution. You were given the same solution, so you can also verify the solution efficiently, right? So, okay, yeah.
What happens to problems that cannot be verified in polynomial?
Okay, so that's a good, right. So, okay, so the question there is, are there problems not in NP that you cannot verify in polynomial time? Do you have any suggestions for that? Yeah.
What's the best move to play in a board of chess?
Okay, so the answer is, what's the best move to play in a board of chess? That's a problem which is, which you can't verify in polynomial time. Yeah, that's a good question. That's a good answer. So games, typically, if I give you a game and I tell you that it's a win for one of the players, right? That's something where you can't verify the answer in polynomial time. But there are other ones. Like, for example, let's look at just a simple variant of what we had here. So we talked about 3 coloring. So let me see. I'm going to change this problem a little bit. So I'm just going to ask for, let's call this number of 3 coloring. So here you're given a graph, and what you need to output is not just one coloring. You need to output the number of colorings. Your solution is the number of colorings, number of different colorings. Okay? So this is a problem where you're counting the number of solutions instead of asking for one solution. And this is actually, you can see that it's not verifiable, because if I give you a graph and you tell me the number of colorings is 10 million or 2 to the 100 or whatever it is, how would you verify that number? The only way to verify that number is to actually find the colorings yourself. And that you can't do in polynomial time, right? Or we don't know how to do those things in polynomial time. So just a slight variant where you count the number of solutions is not in NP. So the examples of problems not in NP would be right, number of colorings, right, when you count the number of solutions, or the other suggestion was games, right? When you have a game and you ask what's the best move in a game, or does white win? Does white or one of the players, black, have a winning strategy? This is called solving a game, and both of these are much harder than NP. You can't even verify the solution. I mean, of course, there are problems for which you can't even solve in any sense, like things like halting problem, which are way beyond this. But these are some natural ones, which you can, in principle, solve in exponential time, but not in NP. Okay, but there are problems which are almost seem like they're in NP, but they're not. So let me get to that. Okay, let's get to that. Okay, so, all right, so let me show you another problem in NP before I get to that. So this is Hamiltonian. So here the input is a graph, and the solution is a cycle containing all vertices exactly once. So this is the Hamiltonian cycle problem, or it's also in the book referred to as Rudrata cycle problem. So you're just given a graph, and you want to know if you can go through every vertex and come back without repeating any vertex, right? Okay, so that's a Hamiltonian cycle problem. And is this in NP? Does the problem seem to be in NP? Do people see why it's in NP? To check that if it's in NP, you just need to check if I give you the graph and I give you the solution, you can efficiently verify it. It's usually fairly easy. In this case, I give you the graph and I give you a cycle. What do you need to check? You need to check that the cycle goes through every vertex exactly once, and all the edges used in the cycle are in the graph, right? And so both of these, you can do it in linear time. You just go over all the vertices and go over all the edges and edges of the cycle, and you're done. So it's nearly a linear time algorithm to check if the answer to this. So that's why this problem is in NP. Okay? Okay, so let's now move to a related problem. It's the minimum TSP. It's the TSP stands for traveling salesman problem. Okay, so what is minimum TSP problem? Well, the input is a graph. Okay, and what you have is this graph has edge weights. So you have edge weights. Okay, and what you want is, this is like minimum spanning tree, except you want a tour, right? You want a tour of minimum cost. Now, what is a tour? A tour is nothing but, it's just a cycle that goes through every vertex exactly once. So what you need to do is you need to start at a vertex, go through every vertex exactly once, return back, and you want to minimize the total cost of all the edges that you traverse. So you want a big cycle of size n, right? You have to go through every vertex exactly one. You just have one big cycle of length n, right? It has n vertices, and you want to minimize the total cost of the edges on the cycle. Okay? So that's the minimum TSP problem. So is this problem in NP? Do people see the issue? The issue is, right, so I give you the graph with weights, and then I give you a solution, and I claim it's the minimum cost TSP tour. Now you need to check whether I'm saying the truth, whether it's the actual minimum cost tour. How do you check? Because you can check, of course, that it's a valid cycle, but you cannot check that that's the minimum cost, because minimum cost means it's smaller than all other n factorial different TSP tours. So this problem is not in NP. As I've defined it, it's not a problem in NP because there's no obvious way to check the solution. Okay, this happens quite often in optimization problems. If you have an optimization problem like a minimization or maximization, it's usually not obvious how you would check that the answer is minimum or maximum. Okay? But this problem is a close, there are close cousins of this problem which are in NP. Okay, so let me define a related problem. So this is called budget TSP. Okay, what is budget TSP? Well, the input is, again, graph with weights. And the goal, and a budget. You're given the input is a graph with weights and a budget B. And the solution is a tour with cost less than or equal to B. Okay, so it's essentially sort of looks like the same problem, but somewhat different in that the input specifies the budget that you can have, and you want to see if there's a tour whose cost is less than B. Okay, the solution is a tour of cost less than b. This is really easy to verify, right? You just check that the tour is a tour, it is a cycle on n vertices, and you check that the budget is at most b. The total cost of the tour is at most b. So it's easily a problem in NP, right? Okay, but it's very closely related to the min TSP in that, in effectively, if you want to understand how difficult the problem is, you could say min TSP and budget TSP are roughly the same difficulty. I claim that if you can solve min TSP, you can solve budget TSP. Does that make sense? Because what do you do? Well, you can find the smallest tour. If you can find the smallest tour, and then you can just check if it's smaller than your budget. If it is not, there is no other tour anyway. If it is, you output that. So if you can solve min TSP, it's really immediately you can solve budget TSP. I'm going to say if min TSP is easy, or let me not say use the word easy. Let me use the word if min TSP can be solved efficiently, then budget TSP can also be solved efficiently. Okay? It's just a slight variant, right? And the converse is also true. If you can solve budget TSP, you can also solve min TSP. Why is the converse true? Does anyone have an answer? Right, suppose I can solve budget TSP. How would you solve min TSP? Right, let's say, suppose I give you an algorithm to find a tour of cost less than b if there is one. Okay, can you use it to minimize? Find the cost of the smallest cost? Yeah.
You could try to find the budget TSP on budget 1, or like whatever your smallest increment is, and then try again with your each smallest increment.
Right. So you could, basically you can vary the budget and find the smallest budget at which you can still find a tour. Right. For instance, you can do binary search. You could say, okay, give me a tour of budget, whatever, some really large number, B. Okay, it gives you a tour. Okay, now you ask, is there a tour of cost less B over 2? Okay, you do binary search on the value of B to find a tour of the minimum cost, if there is one. Yes?
Just to clarify, so if like say you didn't do binary search and sort of naively just did, kept updating like budget by some delta, that wouldn't be polynomial then, right?
Okay, yes. The question was, what if we didn't do binary search on the budget but just incremented it? That wouldn't technically be polynomial time in many settings because B could be just a number which is really large. It could be pseudo-polynomial time. But if you do binary search, it will be polynomial time. Yeah?
So if we know that min TSP is not in NP, that means it's not in P. But if we have an efficient solution for budget P, that would mean that min TSP is also in P.
Okay, so...
Could we just say that budget TSP can't be in P?
Right. So good. I think you caught me on something very important. Right. Yeah. Okay. So this is not technically proven or true. Right. So what do I mean? What do I mean? Well, when I say min TSP is not in NP, I just mean that nobody knows an algorithm to verify if a TSP tour is the smallest. Okay? But of course, it could be that min TSP is in P, or maybe P is equal to NP. And then all of these problems are in P. All of them are solvable and then, of course, verifiable. Right? So in that sense, when I guess I should qualify. When I say min TSP is not in NP, I mean assuming NP is not equal to P. Not even that. I'm even saying nobody knows an algorithm to verify min TSP. Yeah.
How would the algorithm for variance budget work if the budget is an arbitrary real number?
Right. So the question was, how would you vary the budget if the budget is an arbitrary real number? I think the basic idea is to do binary search. So you start with 2 to the n squared or whatever value, and then you do a binary search. And of course, there are issues with the weights being real numbers, and what precision you want, and so on. We'll sort of push it under the rug now. But basically, the point is that you're doing binary search on n factorial different tours. There are only n factorial different tours. So in some sense, there are only n factorial different numbers on which you're doing binary search. So in some sense, you don't need infinite precision. But we'll ignore the precision issues for now. Okay, so this is min TSP, budget TSP. Okay, so there is another version of problem that you would see if you look up NP in textbooks apart from ours. NP is defined in terms of decision problems instead of search problems. So these are problems where the answer is a yes or a no. Not a decision problem is just a problem where the answer is yes or a no. Whereas a search problem, as we've defined it, is I just give you an input and you give me a solution, which could be some sequence of bits or a tour or a tree or whatever it is. A search problem is where the output is a string of some length. A decision problem is where the output is just yes or a no. Okay? And typically, NP is defined in terms of search problems. And so there's a search version of budget TSP. Right? Let me call that decision version of budget TSP. What am I saying? There's a decision version of budget TSP. I'll just call it decision budget TSP. Okay, this is a kind of a fairly closely related one. Again, you have the same setup, weights, and then you have a budget B. Okay? And your solution that you're looking for is just a yes or no answer. You're asking, is there a tour of cost less than B? Okay? So it's a subtle difference. Just over here I said, give me a tour of cost less than B. Over here I'm saying, is there a tour of cost less than B? Okay? Just a 0-1 answer. So, okay, so we've seen 3 versions of the problem now. One is the optimization version, which is here. This is the optimization version. You want to minimize. Okay, this is the search version. And then this is the decision version. So sort of there are 3 versions of the problem, but they're all very closely related to each other, right? Typically in this class, where we'll be talking about search problems, so we'll be looking at budget TSP. But as you can see, you can prove that they're all related to each other. Okay? Though proving that decision, if you can solve the decision, you can also solve search, is actually a slightly interesting exercise. You should try to do it. Maybe part of the homework. Okay, so that's good. Okay, so we've seen a few NP problems. But as you can see, the definition of NP is very, very broad. I'm just saying whenever you can verify the solution, it's an NP problem. So there are many other problems which are in NP. So for example, let me say the following. Let's talk about breaking RSA. Okay? Right? Breaking an encryption scheme. That is a problem which is in NP. Yes, question?
Quick question. So for the last one, like the decision budget TSP, I don't know if you mentioned, but like, was it the PNP? Like, what was the classification for that?
Okay, the question is decision budget and decision budget TSP, is this in NP? Well, this is in NP, and in fact, this is in the most standard notion of NP which you find in most textbooks. Okay, this is the NP. This is the decision NP. Okay, that's the most standard version of NP. In this class, we'll be defining everything in terms of search problems. So in a sense, this is when I say NP, I mean search NP. Okay, yeah. Yeah, oh, right. 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 So okay. The question is, how do you verify the answer to decision and decision budget TSP? Okay. So I'm going to say something, but if you don't have to follow it, because we won't be using this definition of NP in the typical definition of NP, the standard definition of NP that you'd find in many books. An NP problem is always a decision problem, and you can verify the answer to that given a proof for the answer. So meaning someone would write down a tour of cost less than B, and then you verify that the answer is yes. So so these are small distinctions in the definitions. They don't really matter so much for the under basic story that we have. But it's good to know that there are 3 versions of the same problem that you can talk about, and these are all related. Okay? Okay. So let's, okay, I think we have about 5 minutes. Let me just show you why breaking an encryption scheme, like an RSA scheme, is also a problem in NP, and what that means. Okay? So what is it? Well, what is RSA? Let me just say, so you have Alice and Bob, right? It's a public key encryption, right? Alice releases a public key. Okay? A public key encryption is where anybody can send a message to Alice because she released a public key, but only Alice can read the messages that she receives. So Alice releases a public key, and Bob has to send some message, so he can encrypt using the public key. So he can use the public key and encrypt his message M, and he sends the encryption on the channel. Okay, and Bob, what Alice does is she just receives the encryption and decrypts it. Right, that's the setup. Okay, so now what does breaking RSA mean? Well, there is Eve or someone who's looking into the conversation, and he wants to figure out what the message is. That's what breaking is. And so what does that mean? Well, he gets, what is the input for breaking RSA? Well, he gets to see the public key. Right? He gets to see the public key, and he gets to see the encrypted ciphertext or the encrypted text, right? Which is I'm just going to write as is, encryption of P, K, and M. Right? This is what he sees, and his solution that he cares about is a message M. He wants to recover the original message M. Okay? That's what breaking RSA would mean. Okay? Now, why is this an NP problem? Well, this is an NP problem because what does a verification algorithm need to do? It gets the input. What's the input? Well, it's the public key and the encrypted message. Okay? It gets the input, and it gets a solution, which is basically the message. And it needs to verify that indeed that was the message. Well, that's just easy. Why? Because encryption is easy. What does it need to do? It gets the public key and the encrypted message and the message. All it needs to check is if you encrypt the message, you get that ciphertext. right? It just needs to run the encryption algorithm on M and PK and see if that's what the ciphertext looks like, right? I mean, this is sort of intuitively clear if you look at passwords or something, or whenever you have there's some secret, and guessing the secret is usually like an NP problem, because once you guess the secret, many a times you'll be able to verify it. So breaking RSA is in NP. Okay. So let's go back to one of the first questions that was asked in this lecture, which was, okay, so now we have two classes of problems. We've seen examples of both. You have P, and then you have NP. And literally the $1 million question is whether P is equal to NP. Okay? It's literally a $1 million question, because if you resolve it either way, there's a $1 million prize on it. And it's probably the hardest way to make your $1 million. But it is what it is. Yeah, this is I ignored I didn't give you the formal definition of P and NP, but this is a very formally defined mathematical problem. It seemed like I was, but it's a very formally defined problem in math, and we don't know if P is not equal to NP. And it's really an amazing question, because all of us have this experience that if you're doing a homework or we're solving a problem, that checking a solution is much more difficult, much easier than coming up with a solution, right? Just, listening to music is much harder than writing music. Writing solutions is much harder than checking somebody else's solution, right? So this is very natural notion of verifying is easier than coming up with something. And it's one of the amazing things that in computer science, we've been able to formalize this as a clean mathematical question, which we don't know the answer to, right? It's a very clean mathematical question, and we'll see more about it in the coming lectures.